Hi everybody, today we're going to talk about logistic growth functions, which are also called S-curves. To start, we're going to think about a spread of a virus. It usually starts with a few people and quickly spreads to more and more people in the population. So far, when we've been talking about modeling functions that spread quickly, we've said that they were exponential. Notice this graph looks like a J. If we try to model the spread of this virus using an exponential model, we would have a J-shaped curve. But in reality, there are limiting factors of the population that generally slow down the growth. This means the spread of the virus is very quick at the beginning, but over time, the rate of growth will slow. Our J-shaped curve levels out to an S-shaped curve, which we call a logistic growth model. Logistic growth functions generally have the form f of x is equal to c over 1 plus a e to the negative bx. A, B, and C are all going to be constants, meaning that once we have this value for our particular model, they're not going to change. And we'll talk a little bit more about what A, B, and C represent. For now, think about B as being the rate of growth for the logistic growth function. Let's dive in by looking at an example. The logistic growth function f of x is 50,000 over 1 plus 499 e to the negative 1.2x models the number of people who have a virus x weeks after its initial outbreak. To start, let's figure out how many people had the virus when the outbreak began. This corresponds to when x is equal to 0. We'll plug 0 into f of x, which gives us 50,000 over 1 plus 499 e to the negative 1.2 times 0. Because anything times 0 is 0, we have 50,000 over 1 plus 499 e to the 0. E to the 0 is 1, which gives us the denominator of 1 plus 499, which is just 500. Now we can reduce 50,000 over 500 to 100. So when the virus began, and when we noticed that we had an outbreak, 100 people were already sick. Let's figure out when 1,000 people have the virus. To find our solution, we set f of x equal to 1,000. Given 1,000 is 50,000 over 1 plus 499 e to the negative 1.2x, I want to bring the part with the x out of the denominator, which means I should multiply it over to the left. Now that I have 1,000 times 1 plus 499 e to the negative 1.2x equals 50,000, I'm not going to distribute the 1,000. Instead, I'll divide by it. 50,000 over 1,000 gives us 50. Then we can move the 1 from the left over to the right to give us 49. Eventually, we're going to have to use the natural log, but remember we never do that before we isolate the e. This means we need to divide by 499. Now we have e to the negative 1.2x is 49 over 499. When I apply the natural log to both sides, I have the natural log of e to the negative 1.2x is the natural log of 49 over 499. The left side is just negative 1.2x, the right side keeps the natural log. To get x alone, I'll divide by negative 1.2, which says x is the natural log of 49 over 499 divided by negative 1.2. We plug that in our calculator to get about 1.93 weeks, which we would probably round to about 2 weeks. Part C says how many people will become ill overall. Overall means time is increasing, so x is getting bigger and bigger. To figure this out, we want to kind of stop and isolate the part with the e. I rewrote the function as f of x is 50,000 over 1 plus 499 divided by e to the 1.2x. I want you to think about what's happening as x gets bigger. Because e is exponential, it's getting larger and larger and larger. 499 is staying the same. So I put this in my calculator and only took the 499 over e to the 1.2x. So at 0, we can see it's 499. At 1, it dropped to 150. At 2, it's 45. At 10, it's 0.003. And at 20, I get 1.88 times 10 to the negative 8, which basically says our value is 0. So this little piece of the function is getting smaller and smaller. Because of that, the 499 over e to the 1.2x goes away, and I'm looking at 50,000 over 1, which is just 50,000. We call 50,000 the limiting capacity of our function. So when we think back to our original model of f of x being c over 1 plus a e to the negative bx, c stands for the limiting capacity of any logistic growth model. Let's try one more example. This time I have a of t is 2.3 million over 1 plus 24 e to the negative 0.32t. This models the number of people who have filled out the census in a state 2 weeks after the census started. So the first question is, how many people filled out the census initially? We already know initially means we plug in 0. I have 2.3 million over 1 plus 24 e to the negative 0.32 times 0, which tells us we have 2.3 million over 25, which turns out to be 92,000. So as soon as the census came out, 92,000 people turned it in. Part B says how many people have filled out the census 3 weeks after it began. This time, we take the number 3 and we plug it into our model. We have 2.3 million over 1 plus 24 e to the negative 0.32 times 3. This comes out to 217,549.1786. We can't have part of a person, so we're going to get rid of the decimal and just leave it as 217,549. Our last question says, what is the carrying capacity of the model? Carrying capacity will be that value of C that's in the numerator. So you don't have to do any work. You know it's equal to 2.3 million. Remember, use your calculators to help you as you solve these problems. Because E has 2 parts in the exponent, both the rate and the time, you want to make sure you put parentheses around that part so that you get the right answer.